We are moving on to the last third of the course now, and now is when we're basically going to be talking about two variables at a time. So we're going to be jumping back and forth in the book a little bit because the topics we're going to be talking about are introduced early in the book in a descriptive sort of way, and then readdressed later in the book in terms of inference. It's like, okay, that's what we saw in our sample, we described what we saw, now what do we think is true in the population? So we'll be jumping around a little bit. We'll be starting here where we have two categorical variables. So smoking, non-smoking, cancer, no cancer, that sort of thing. So categorical variables. And we'll be putting them in a two-way table. Chapter 3b, where we're starting, is describing what we've got. What do we see in the relationship between those two categorical variables? What do they look like one at a time? And then we'll be jumping to chapter 26, which is the chi-square test, saying, okay, that's what we saw in our samples. What do we think is true in the population? Then we'll be jumping over to where we have two quantitative variables. So quantitative, things like height and weight and age, a number that means something. So we'll start with correlation. What's the relationship between these two quantitative variables? Is it positive or negative? Is it strong or weak? What does the relationship look like? And then we'll be moving on to chapter 8 with regression. If we want to predict one quantitative variable from another, or if we want to see the rate of change, the slope, how does the change in one variable affect the other? And then inference. Inference, chapter 27. We'll be taking both correlation and regression and saying, okay, that's what we saw in our sample. What do we think is true in the population? And then we'll be ending up here with analysis of variance. That's where we have one categorical variable and one quantitative variable. So it's like the two-sample t-test. The two-sample t-test, we compared two groups on a mean. Now we will not be limited to two groups. But we'll still be comparing groups on a mean. It's called analysis of variance, and that's chapter 28. And then we're at the end of the semester. So that's where we're headed, starting over here with two categorical variables. So today we'll be doing chapter 3b, the second half of chapter 3. So with two-way tables, we have two categorical variables. And for this example, we're going to talk about and look for a relationship between what college you go to, whether you go to Calvin or any rival college. So you can pick your own favorite rival college. I'll pick mine, okay? And we wonder if there's a relationship between what college you go to and whether you're kind to animals and small children. Now I suppose that could be quantitative. You could put it on a scale, how kind you are to animals and small children, but we're just going to say yes or no. Okay, so we do have two categorical variables, what college you go to and whether or not you're kind to animals and small children. So when we have a two-way table like this, we start by doing exactly what we did in the first half of chapter 3, describing what we've got one variable at a time. So what percent overall went to what college? What percent overall were kind? So we need some numbers in the totals, the margins. So let's say we have 200 students total, 100 from Calvin, 100 from the rival college, and let's say that 120 are kind and 80 are not. So now we're going to describe our variables one at a time. These are called the marginal percents or the marginal distributions because we're getting the numbers from the margins, the totals. So if we look at college first, well, out of our 200 students, 100 came from Calvin, so 50% are Calvin students, and 50% come from the rival college. And whether you're kind, well, 120 are kind out of the 200, so 60% are kind, and not kind, 80 out of 200, 40%. So we have described our sample. What percent came from each college? What percent were kind and not kind? These are the marginal percents, and that's how we start. We want to describe our sample. What have we got? What have we got? But these marginal percents tell us absolutely nothing about whether there's a relationship between what college you go to and whether or not you're kind to animals and small children. And that's what we want to know next. So first we described our sample. Now we want to see if there's a relationship. Those are called the conditional percents or conditional distribution that we're going to use for that. Now we need numbers in the table, because we're going to take the table either row by row or column by column, and we're going to look for differences. We're going to look for differences. So first, let's say we have those numbers in the table. Well, we'll take it row by row because we want to compare Calvin to the rival college. So among Calvin students, we have 100 Calvin students, and of the 100 Calvin students, 60 are kind. So 60% are kind and 40% are not. Among the rival college, we have 100 students in the rival college, 60 of them are kind. So for both Calvin and the rival college, 60% are kind and 40% are not. This means that college and kindness are independent. Independent. There's no relationship, there's no difference between Calvin and the rival college in the percent that are kind. So college and kindness are independent. You're just as likely to be kind if you go to the rival college as if you go to Calvin. Okay? They don't have anything to do with each other. They're completely independent of each other. But now let's change the numbers in the table a little bit. So we'll leave the numbers on the outside the same. And we'll need new ones down here if we change the numbers in the table. So these are conditional percents, conditional on limiting ourselves to one group or another. So now let's do this. So everything adds up. 100 Calvin students, 100 rival students, 120 kind, and 80 not. So now let's look at the conditional percents. So first we condition on Calvin students. Well, of the 100 Calvin students, 100 are kind. So 100 out of 100. So 100% are kind. And now let's look at the rival college. Well, out of the 100 students from the rival college, sadly, only 20 are kind. That is very too bad. Now, college and kindness are not independent because being kind depends a whole lot on which college you go to, that these are not independent. These are associated or related or dependent, but they're not independent. They are related somehow, that you're much more likely to be kind if you go to Calvin than if you go to the rival college. So when we have a two-way table like this, we first look at the marginal percents. We first describe them one at a time. Half the students came from Calvin, half from the rival college. 60% were kind, 40% were not. So we look at the outside, we describe variables one at a time. Then we look at the numbers in the table. We take things either row by row or by column. We could have looked at this way too. Among students who are kind, 100 out of 120 came from Calvin. And among students who are not kind, all of them came from the rival college. And that would tell the same story, right? So usually either the row percents or column percents give you a good picture of the relationship. In this case, I thought the clearer picture was if we broke it up by college. We thought that college may have some effect on whether you're kind to animals and small children. And in fact, that's what we saw. Since 100% of Calvin students are kind, but only 20% of the rival college students are kind. So they are associated. So in the conditional percents, of course, we're looking for differences, right? When we had 60% of Calvin students kind and 60% of the rival college students kind, there was no difference, no relationship between the two. Kindness and college were completely independent. We only saw that there was a relationship when these percents differed. Among Calvin, 100% were kind. Among the rival college, only 20% were kind. So when your row percents or your column percents differ one from another, then we think that there's a relationship. So that's the first part of chapter 3b. The second part is called Simpsons paradox. Simpsons paradox. Simpsons paradox is when there's a certain relationship that holds And once you take a lurking variable into account, you realize that the relationship is very different from what you thought. So just for an example, let's say I gave you two basketball players. Let's say we've got Bob, and let's say Bob makes 80% of his shots in basketball. And let's say we've got Sue, and Sue makes 30% of hers. And I would say, who's a better basketball player? And you would say, clearly, Bob's a better basketball player. He makes 80% of his shots. Sue makes only 30% of hers. Now, what if I added the lurking variable of what kind of shot they tend to take? So let's say Bob only tries layups, and Sue only shoots from the half-court line. Well, now things are different, right? Now the question is, which one is the better ball player? I mean, maybe you'd want to stick with Bob anyway, because hopefully he'd make a whole lot of baskets with layups. But it certainly doesn't make it clear that Bob is definitely the better basketball player. I mean, the fact that Sue can make 30% from the half-court line is very impressive. So we added a lurking variable. The relationship was not as simple as we first thought. It was not as simple as we first thought. So the example in your notes is looking at the percent of two different airlines that are on time. The percent in two different airlines that are on time. So at first glance, we see, so we're going to compare America West and Alaska Air. And these are data from June 1991. June 1991. So overall, for Alaska Air, let's see what percent were on time or delayed. So delayed, 501 flights delayed out of a total of 3775 flights. So 13.3% of the Alaska Air flights were delayed. And the other airline we're comparing it to is America West. America West had 787 delayed flights out of 7,225 flights. 10.9% delayed. So the question is, which airline should you fly, all other things being equal? Well, clearly America West, right? You're more likely to be on time if you fly America West. Well, Simpson's paradox says you should always think about lurking variables, that the relationship may not be what you thought. It may not be as simple as you thought. So in this particular case, what appeared to be a simple relationship, America West, you'd want to fly because they're more likely to be online than Alaska Air. There's a lurking variable of what airport they tend to fly to. They tend to fly to. So let's look at it split up by different airports. So we've got Los Angeles, Phoenix, San Diego, San Francisco, and Seattle. Alaska Air at Los Angeles, 62 out of 559 were delayed. That's 11.1%. America West, 117 out of 811 were delayed. That's 14.4%. So overall, Alaska Air had a higher delayed rate. But if we look at Los Angeles, America West had a higher delayed rate. And in Phoenix, 7.9% to 5.2%. Same thing in Seattle. America West, 14.5% were delayed versus San Diego for Alaska Air, 8.6% delayed. Same thing for San Francisco and Seattle. In fact, if you look at each city individually, in every case, Alaska Air did better. They had a lower delayed flight rate than America West. So the question is, how can this happen? How can this happen? That clearly, when we just combine all the data, Alaska Air did worse, but when we break it up by airport, Alaska Air did better at every single airport. Well, the key is recognizing where they fly. Alaska Air tends to fly to Seattle. If you look at the flights, Alaska Air, the number of flights to Seattle, 2146. So a whole lot of flights were to Seattle. America West, many of their flights were to Phoenix. Well, if you think about Phoenix versus Seattle, Phoenix, blue skies, sunshine every day of the year. Seattle, very cloudy, harder to be on time. And so Alaska Air tended to fly to places that were harder to be on time to, especially Seattle, whereas America West flew to places where it was easier to be on time, specifically Phoenix. So that's how the overall rate could look worse for Alaska Air, even though at each individual airport, Alaska Air did better. It's because the bulk of their flights were to a difficult airport and a bulk of these flights were to an easy airport. So Simpson's paradox says you can look for a relationship between two variables. In this case, Alaska Air has the worse on-time rate. But you should always be thinking about possible lurking variables, because you may have a situation like Simpson's paradox where the relationship you thought you had is completely reversed once you take into account a lurking variable, and the relationship may be backwards of what you thought.